Okay, so this is, I think, lecture 9 of number theory. We had a coding assignment, which I know has kept several people up tonight. I've gotten several emails from people who have been struggling on this. This is why I warned you all earlier that this is going to be a tough assignment. One of the skills I want you to get out of this class is the ability to write code and investigate problems. So I will happily have another coding review class sometime next week, so we can talk and review these ideas. Several of you have talked to me about the difficulties of trying to do this coding in other languages other than Mathematica. So Mathematica has a lot of number theoretic functions built in to make these questions easier to investigate. And I think, Alex, you said that you can import Mathematica commands to C. Okay. Okay, and Fortran. Oh, God. I have not used Fortran in decades. It is nice to know that if you want to go that route, it is still possible. Okay, so the purpose of this is to get the skill of being able to do numerical simulations. And if you can do that, you can get a huge sense of what's going on and make conjectures. So the homework problems for next week involve a huge sequence of steps to prove a great result. That the goal for the homework is to prove that Z mod PZ star is cyclic. Now the question might be, why do you care that this is cyclic? So remember that this is the set of numbers 1, 2, 3, ... p minus 1, where we're doing all operations modulo p. So remember, because we have some guests here today, x times y is the value we get when we reduce mod p. So if you think of clock arithmetic, on a clock, every time you increase by 12, you come back to where you started. So 10 plus 5, you might say it's 15. And if you're in the military, you might have to say it's 15. But you can also say it's the same as 3, because 15 and 3 differ by a multiple of 12. So why would we care about this result that it's cyclic? That means that there is some g, such we can write this as 1g g squared ... g to the p minus 2. So the purpose of this is that if we have an understanding of what a group looks like, maybe we can exploit that. Now, how many of you have actually seen this result in an abstract algebra class? Okay, so you've actually proved this. Okay, do you remember how you proved this in abstract algebra? No. Okay, I never took abstract algebra, so I don't remember how. I know I taught abstract algebra twice, but that's not quite the same thing. So does anybody remember how they proved this in abstract algebra?
I think you proved that there isn't one, and it causes the problem.
Okay. But the fact that nobody seems to be that sure about how they did it in abstract algebra means I don't have to worry about anybody just using an abstract algebra proof on the homework. And what you'll do is you'll go through a guided set of homework problems that will give you a bunch of good number theory stuff about this. So I will actually have you do this for very special primes. I'm going to assume that p minus 1 is square free. So what that means is if n squared divides p minus 1, then n has to be 1. So p minus 1 can't be a multiple of 4. Is it possible that p minus 1 could be prime? Is there any way p minus 1 could be prime? Only if p is 3. So one of the nice things that Williams does is we have class exchanges. So I've been visiting Professor Morrison's classes this week. He's visiting mine. And he's been very good when he lectures that he always makes sure he remarks that if the characteristic is 2, if the prime is 2, things might be a little different. So for us, maybe if p is 2 or 3, things could be a little bit different. Well, okay, if p is 2, it's kind of trivial. There's only one element. If p is 3, it's also not so bad. But we have to be a little bit careful about those cases. So we might want to be studying large primes, primes that are at least 5. Okay? Now, could p minus 1 be prime if p is a large prime? Okay, why not?
P minus 1 would be even, and then
Good, so p minus 1 would be even. Now, it's possible that maybe 2 is the only prime that divides p minus 1. And it turns out these are called Sophie-Germain primes, and they were very useful in early proofs towards Fermat's last theorem, where people were able to show that Fermat's last theorem actually held for Sophie-Germain primes. So if the only two that divides the only prime that divides p minus 1 is 2, things are actually very nice. What we're going to see today is that knowing the structure of these groups helps us answer questions. And so it's very easy to just keep proving results in number theory for the sake of proving results. I want the big picture. Why do we give a damn? Okay? So at the end of the day, you can say, well, why do we give a damn about what you give a damn about? And at some point, it has to stop somewhere. You have to just say, I find this interesting. One of my research students many years ago was giving 3 reasons at a conference why we cared about something. This was an undergraduate research conference. The first 2 were highly technical, and the third was because my advisor likes it. And that's a really good reason at times. So this is a number theory class. Hopefully you care a little bit about numbers. Which kind of numbers do you care about the most? Primes, right? We're allowed to discriminate here. So we like primes. And so pi of x is the number of primes p less than or equal to x. And we want to understand this. We've given a couple of proofs that this set is infinite. We gave Euclid's proof, which is one of the oldest proofs in mathematics that's still being used. Copyright expired over 2,000 years ago. We can all freely use it. But there's still open questions related to Euclid's method. Have you seen Euclid's proof? So what you can do is you can then construct, as you multiply them, what is the smallest prime in the new prime that you get by Euclid's method that's not already on your list. And this is called the Euclid-Mullen sequence. We don't even know 60 terms of it. And it's highly oscillatory. We don't know if every prime appears in the sequence. There's a lot of great stuff about that. Well, the next thing we might ask is pi ab of x. And this would be the number of p prime, p congruent to a mod b. So we gave you a homework problem earlier where we showed that there are infinitely many primes congruent to 3 mod 4. It turns out we don't have an elementary way of proving that there are infinitely many primes congruent to 1 mod 4. And you could ask, which A and B do we have elementary ways of proving the infinitude of primes of that form? I'm going to ask an easier question. Given A and B, is there at least one prime P congruent to A mod B? Any thoughts? Will there always be at least a prime? Okay, why not?
Because if A is composite and A is a factor of B.
Okay, good. So if A is a composite number and A divides B, we're dead. If A is prime and it divides B, there's at most one prime. Well, we're only looking for one prime, so we'd be done. So we know that there are some A and B where this will fail. Interestingly, this is the only problem. If A and B are relatively prime, then yes. Now, to prove this in general is extremely hard. The proof, it's called Dirichlet's theorem. It's one of my favorite theorems in mathematics. Beautiful result. And the way it works is it's the tactical nuclear strike. I want to prove that there is at least one prime congruent to A mod B. What we show is that this is approximately equal to the number of primes up to x divided by phi of b. So remember, phi of b is the Euler-Toscan function. It counts how many residue classes are relatively prime to b, how many numbers up to b are relatively prime. These are the candidates for A. And what it's saying is, to first order, the primes fall evenly in all these classes. And since pi of x goes to infinity, this goes to infinity, and in fact, not only is there infinitely many primes, but there's the right number of infinitely many primes. To first order, they're all the same. Therefore, there's at least one. This is enormous overkill. I just want one prime. And the only way I know how to prove one prime is to prove that essentially in the limit it's the right infinite fraction. If you can find a better way of doing this, I will give you an A+ for the course. In the problem-solving class, I was only willing to give an A for something. This would be an A+. One of my colleagues, Ria Murty, has a really nice paper on when can you elementally prove that there are infinitely many primes. When does Euclid's argument generalize? And if you know what Erdős numbers are, my Erdős number of 2 is through him. And in fact, it might be because I was embarrassed that my Erdős number was 3 and asked him, can I please write a paper with you? So I'm hoping that you will consider this a sufficient motivation, that I want to understand when there are infinitely many primes congruent to A mod B. I want to understand how primes work in arithmetic progressions. If I look at a structured set, what can I say about that? If you do not consider this an interesting question, then I lose the motivation battle. At the end of the day, you have to have something that excites you, something that motivates you, something that pushes you forward to investigate. And so I'm trying to justify what we're doing by looking at this question. So there is a huge amount of material in Chapter 3 on quadratic reciprocity. And right now, I'm leaning towards not giving a proof of quadratic reciprocity. So quadratic reciprocity. So we define PQ. This is our quadratic symbol, to be 1 if P is a non-zero square mod Q, 0 if P is congruent to 0 mod Q, and -1 otherwise. And so it's a way of telling if a number is a square or not a square mod P, or mod Q, depending on which one's on the bottom. And here, P and Q will be primes. There is a generalization when P and Q are not primes. The generalization is the Jacobi symbol. What's really nice is when I'm calculating this, I don't really need to understand P that well. What's the only thing I really care about this prime if I'm calculating this? So I'm trying to figure out, is there a number that squares to P mod Q? But I claim I don't really care about all of P. I can reduce things a little bit. Instead of looking at P, what could I look at? P mod Q. This is the same as P mod Q over Q. And so this reduces it, so now the top is at most the bottom. And the quadratic reciprocity, I'm not going to state it, is it relates PQ to some relation of QP. And I don't want to state it in case you haven't read all of Chapter 3, though you're supposed to, just so it's a little bit of a surprise as to what comes here. It's actually going to be just a plus or minus 1. It's going to just depend on P's and Q's. What this tells us is that we can keep flipping things. And so we start off with P and Q. Let's say P is larger than Q. We flip. Then we reduce Q mod P. Then we flip. Then we reduce boom, 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 boom. So even if we don't understand why we might care about quadratic reciprocity, it's at least fast. Okay? It may not be useful, but it's at least something we can compute quickly. I think one of the homework problems due today was Wilson's theorem, to show that if n minus 1 factorial is congruent to 1 mod n, n must be prime. This is a deterministic prime test. It is also horrendously slow. There's no good way to calculate n minus 1 factorial. But in Fermat's little theorem, we saw that there is a really fast way to compute a to the n minus 1. We can use fast multiplication. We can do that in logarithmic steps. And so even if p is of size 10 to the 200, we can do that in less than 500 steps. That's negligible. That's reasonable. We can use this for e-commerce. Wilson's theorem, we can't. Now, unfortunately, what's the drawback of Fermat's little theorem as a primality test? Okay, what do you mean by it fails? Sometimes, yeah. So sometimes you have numbers, the Carmichael numbers, that pass the test every single time, but aren't prime. So Wilson's theorem is better, but it's so inefficient it can't be used practically. Fermat's little theorem is extremely fast, but it sometimes will not be correct. Now what you could do is you could use Fermat's little theorem to maybe quickly eliminate some candidates. And then when you have a really good candidate, then you do a better primality test that's really slow, but you can do it very quickly now because you're only doing it to one number. So you can still make Fermat's little theorem work. So over here, this is at least a fast process, and there's a nice exercise. I want you to figure out how many steps would it take, do you think, to get all the way down? Any rough guesses?
Seems like it should be similar to the Euclidean algorithm.
Yeah, so it should also be how fast? What's the word?
I'm a little bit sick today.
Okay. I know I had 3 people email me that they were sick today.
Is it long time?
It's log time.
Okay.
It's log time. Right? So this should be logarithmically. I don't care if it's 2 log q or 3 log q. I won't go higher than that because that could sound bad with a Boston accent. But it's log q, some constant times log q. It's really fast. But who cares about something like this? It turns out this is related to attacking Dirichlet's theorem. So the question is, how do we get from something like this to Dirichlet's theorem? And so what I've decided to do is I've decided to motivate a lot of the material in Chapter 3 and then leave to you, if you want, to read the proof of quadratic reciprocity. You know, if there's time and demand in the end of the semester, I'm happy to go back. There are a huge number of proofs of quadratic reciprocity, from counting on your fingers to Poisson summation and Fourier analysis. You know, Gauss had, I think, 8 to his name. Do you remember?
There's a lot.
He has a lot. You know, Gauss really liked this result. And as a rule of thumb, if Gauss likes something, you should like it too. You know, this person had really good intuition on what math matters. And in fact, one of my colleagues, who was a first-year student with me at Princeton, has a Fields Medal, in part because he looked at a question that Gauss had looked at and pushed it further, you know, something that people hadn't really looked at too much over time. There's a lot you can get by going back to Gauss. So what I want to talk a little bit about, and I'm going to try to keep Dirichlet's theorem up on the board as long as possible to just keep you motivated as to why we're doing all this. So we can introduce almost any function we want. It's which functions are useful. So what is my most favorite function to study as a number theorist? Who knows me? Yeah, Professor Mawson, you may speak up. It is the Riemann zeta function. So the Riemann zeta function, and we've talked a little bit about this in class. It's defined as zeta of s is the sum, n goes from 1 to infinity, of 1 over n to the s. And it turns out this is the same as the product over p prime, 1 minus 1 over p to the s inverse, at least if the real part of s is greater than 1. Typically, we write s equals sigma plus I t. I is the square root of -1. This is in some sense bad notation because you're mixing Greek letters and non-Greek letters. But what my advisor said is, until you prove the Riemann hypothesis, you will use Riemann's notation. So not only will I give you an A+ if you prove the Riemann hypothesis in this class, I will get you admitted to Princeton. And probably also get you an honorary doctorate from Williams. I think Williams would like to have a doctorate associated to your name, and just Williams College said whenever possible with your name. Okay, this is one of the biggest open problems in mathematics, is related to the distribution of zeros of this function. It's a nice exercise to show that this function has no zeros when the real part of s is greater than 1. We know it has no zeros when the real part of s equals 1, and it turns out that's equivalent to the prime number theorem to pi of x is about x over log x. the best we can do is the following, and this is just a real aside. Here's 0, here's 1/2, here's 1. We believe all the zeros of the Riemann zeta function lie on the line 1/2. All that we can do is we can show there's no zeros on the line 1, and there's some shape like this whose thickness is decreasing to 0, and it's like 1 over log to a power. And there's no zeros in the small little sandwich area. It's really annoying that in many years of time we have not been able to progress above this. Right. We've given, I think, 2 proofs of why the Riemann zeta function is important in number theory. I think we mentioned the following, that the limit as s goes to 1 from above of zeta of s equals infinity implies pi of x goes to infinity. And the reason is, as s goes to 1, this becomes the harmonic sum. The harmonic sum diverges. Therefore, if there were only finitely many primes, this would be finite. Therefore, there must be infinitely many primes. And in fact, with a little bit of work, you can even get that the sum over primes of 1 over p is about, p less than or equal to x, is about log x. This is because whenever you see a product, what should you do? Take a log. The only time you don't take a log with the product is if you're talking to, say, somebody in 1st or 2nd grade and you're trying to explain to them how to multiply like 3 times 4. Other than a situation like that, if you see a product, especially with many, many terms, you should be taking logarithms. And if you take the sum of n up to x, the sum of 1 over n is like log x. The log of that would be like a log x. That's really where this is coming from. The second proof which we mentioned was that zeta of 2 is the sum of 1 over n squared, and it goes from 1 to infinity, is pi squared over 6, and this is an irrational number. And because that's an irrational number, that also implies pi of x goes to infinity. And the reason is, if you put in s equals 2, this would be a rational number for each prime, and if there's only finitely many primes, the product of finitely many rationals is rational. So because pi squared is irrational, there are infinitely many primes. I actually have a paper where, in fact, some of the students involved are Williams students, where we actually try to exploit knowledge of how irrational pi is to get an estimate of how quickly pi of x goes to infinity. The first proof that I came up with when I was a postdoc at Brown, I had a worse result than Euclid. Euclid shows that the number of primes up to x is about log x. And it turns out I was using a theorem which was actually using the prime number theorem. So using the theorem that says the number of primes up to x is about x over log x, I was able to prove there are at least log x primes, which is really not that impressive of a result. But fixing things a little bit and not using that result, we're able to get very close to the prime number theorem from the irrationality of pi squared. Okay, so why is this important? This is a great function to study. It connects what we want to understand the primes to something we understand the integers. So I think I've done this before. What's the closest prime to 2017? 2017. What's the next prime? Okay, pause. What's the next integer after 2017? Yeah, I think Kayla was here this day and Kayla was rattling them off. And so the distribution of the integers is not that mysterious. It's quite well understood. And the idea is to use knowledge of the integers to get knowledge of the primes. So the idea is maybe instead of studying the Riemann zeta function, maybe we could study other functions that would help us with Dirichlet. Right? So the question is, what functions would be good to study? So the zeta function is defined as this. And the reason we have this product, this is called an Euler product, this is due to the fundamental theorem of arithmetic. The unique factorization of integers. We could more generally look at LSF, which I'll define as the sum, and it goes from 1 to infinity of a sub f of n over n to the s, where I get to choose what these AFs are. And I would also hope that this has some kind of product expansion of something. And I would hope it converges for the real part of s greater than something. So again, the goal of today's lecture is to give you a rough sense of what we're going to study. You could look at choices that don't have a product. We don't like to study them in analytic number theory. We really like the product. And one of the reasons is the log of a product is the sum of the logs. It's very easy to attack. If we don't have the product, we're in trouble. And so we will not investigate anything, really, that doesn't have a product. So the question is, what is a good choice of AF of n? Well, this is probably the simplest choice you could make. AF of n is identically 1. That's a fine choice. What else could we take? And this is where we're going to start looking at these groups Z mod PZ star. So when we do Dirichlet over here, what I want to do now is, instead of taking any A and B, I might choose B to be a prime Q. And the reason I'm choosing it to be a prime Q is that things will be a little bit easier in terms of trying to study the structure of the group Z mod QZ star, where it's a prime. We can prove that this group is cyclic. Okay? The results hold in greater generality. When you became a Sonic student when I was in Princeton in the mid-90s, this was before illegal PDFs, which I know none of you would ever use, but what you had to do is you had to get copies of books, and some of the books were out of print, or you would need chapters of articles. One of the skills you learned was how to use Xerox machines and make massive copies quickly. Of course, we only did this for legal purchases. But one of your things when you became a Sonic student is you had to read Davenport's multiplicative number theory. That was one of your assignments. And if you look at Davenport's multiplicative number theory book, he talks about this problem of primes in arithmetic progression. He proves Dirichlet's theorem. The proof is much easier for a fixed modulus that's prime. The more general modulus, it has a more complicated structure for Z mod BZ star. And the simpler the structure, the more we can use to our advantage. So what I want to do now is I want to define new functions. I want to define characters. And these are going to be maps from Z mod QZ star to complex numbers of absolute value 1. Okay? So it turns out these are extremely useful functions to study. Now, how many of you have taken abstract algebra? Okay. Have you taken abstract algebra? Alex, yeah. Okay. So then I'll just talk to you right now. So one of the things we often like is we like functions that are nice with respect to the group structure. So we would love if chi of G1, G2 was chi of G1, chi of G2, if it preserves this multiplicative structure. And if this is true, we will say it's a homomorphism. And what's nice is the character of the product is the product of the characters. So we multiply first in Z mod QZ star and then apply the map, or we apply the map and then multiply. Either way is the same. We don't have to worry about the order. So I would love to have multiplicative characters like this. Can anybody give me a nice map from Z mod QZ star to complex numbers of absolute value 1 that's multiplicative?
We map like an element x to the element x times the cube root, like cube root of infinity.
So you want to, okay, so let's let zeta of q be e to the 2 pi I over q. So this is a good thing to look at. And what do you want to define? Chi of x to be what?
To be just x times e to the 2 pi x over like x.
Okay, so what you want to do is you want to do zeta q to the x.
Yeah.
And then if we had two numbers, unfortunately, x times y, you're close. That would be zeta q xy, but that's not going to be zeta qx times zeta q of y, because this is going to be zeta q of x plus y. But it's a really good wrong answer. And it'll be very useful for what we're going to do in a moment. So we'll fix this in a moment. But can anybody give me a map that's multiplicative that takes z mod q z star to complex numbers of absolute value 1? I don't care how trivial your example is. Can you give me a map? Map them all to 1. That works, right? Any Simpsons fans here? All right, there's an episode where Bart observes something wrong, and he's not sure what he should do. This is the one, the clam chowder episode. And so he's asking his mother for advice. And she starts talking about one of Bart's uncles who went crazy one day and basically just shot everybody and let God sort it out. It's essentially what we're doing here. Map everything to 1. Will that be multiplicative? Yeah. 1 times 1 is 1. So this is called the trivial map. And we define it basically as chi0 of x is 1. So we always know that that map exists. The question is, what other maps will exist? Right, so I'm going to erase this stuff over here. And so the suggestion of looking at a qth root of unity is not a bad one. We need to just make 2 small modifications so you were almost there. The first is, how many elements are in z mod qz star? There's q minus 1 elements. So again, one of the nice things about this class is there's no set curriculum. There is no class that has this as a prerequisite, which means we have complete freedom to do what we want. So we can spend some time and really think about how you would guess things, how you would build things up. Let's say x, I'm going to use n, because chi of x could be a little confusing to write. Let's say n is in z mod qz star. We have q minus 1 elements. So one of the things you'll show in your homework is n to the q minus 1 is congruent to, well, actually, while you may be showing this on your homework, we've actually already done this. Why is this true?
Because q is prime, so n and q are relatively prime.
So n and q are relatively prime, and so Fermat's little theorem. So this is Fermat's little theorem. So by Fermat's little theorem, n to the q minus 1 is congruent to 1 mod q. So what does this mean? It means chi of n to the q minus 1 must be the same as chi of 1. Chi of 1 is the same as chi of 1 times 1, which is chi of 1 times chi of 1. What must chi of 1 equal? So chi of 1 could be 1. Is there anything else chi of 1 could be?
0, but that's kind of trivial.
Well, 0, it's kind of trivial. But I mean, I allowed you to do something kind of trivial there before. Maybe I'm in a kind of trivial mood today.
But like, it makes everything have to be 0.
So it makes everything have to be 0. The other thing is we said we're mapping to complex numbers of absolute value 1. So since we're mapping to complex numbers of absolute value 1, it can't be 0. So this tells us that chi of 1 has to be 1. But because it's multiplicative, we now get chi of n to the q minus 1 is 1. So what this means is chi of n must be a number which, when we raise to the q minus first power, equals 1. So this tells us that chi of n is a q minus first root of unity. So when you said q, you were just a little bit off. We need q minus 1. So if we let zeta of q minus 1 be e to the 2 pi I over q minus 1, then there exists an L such that chi of n is equal to zeta q minus 1 to the L. then explicitly that would just be e to the 2 pi I L over q minus 1. Okay? So this is wonderful. Because it's multiplicative, this is the only possibility. Okay? Now the problem is we want to figure out what this character does to all the different elements of z mod qz star. But we know it's multiplicative. Wouldn't it be wonderful if it was sufficient to know what the character did to just one element in z mod qz star, and then we get everything else for free? For that to happen, we would love this group to be cyclic. It's cyclic. So it turns out this is actually generated by some element g. It's 1g, g squared, g to the q minus 1. So we know we have a cyclic group. So because we have a cyclic group, now that we use the stuff, what we can do is, if we know what the character does to a generator, we know what it does anywhere. So chi of g to the m is just chi of g to the mth power. So we just need to figure out chi of g. Thus suffices to find chi of g. And from before, there exists an L such that chi of g is going to be e to the 2 pi I L over q minus 1. And in fact, every L is going to give such a character. Each L gives a character. So where does L live? What are the possible values for L? Yes.
Not just like the elements of z mod q.
Well, z mod, okay, so z mod q has how many elements? That has q elements. How many elements do I have here? Yes.
L can exist between 1 and q minus 2.
Okay, so it could be 1, 2, 3, q minus 2. It's possible.
I guess it could be 0.
It's possible that I just accidentally left space.
Oh, it could be 0, I guess, but that would be the trivial solution we had earlier.
Well, that trivial solution we had earlier should be on our list. That's a possible character.
I guess it is a solution.
It's a solution, right? We don't want to throw away the trivial solution just because it's trivial. In fact, the trivial solution is what actually causes most of the action that we'll see in a few minutes. So these are the possible characters. So I can explicitly write down the characters in the case of z mod qz star. In general q, if I gave you a general b, this could be done, but it would be a lot more painful. Okay? But for this particular q, we can do this. And so now we know here are the possible characters. So we have q minus 1 characters. And we have an explicit formula for all of them, which is extremely nice. You know, we can do a lot with this explicit formula. So we're going to use this to get to a sketch of why there are infinitely many primes congruent to A mod Q. So let's consider chi of g to the m. And we're going to sum over all, well, I'll write chi sub L, and we'll sum L goes from 0 to q minus 2. So I'm summing over all the characters. Now, in general, there's a lot of nice ways to prove what this sum is, but because everything is so explicit, I can actually just write down this is the sum. L goes from 0 to q minus 1. Now, I'm calculating g to the m. Okay? So that's going to be e to the 2 pi I L over q minus 1, and then I raise this to the m, so that's the same as just putting the m in here. This is the same as the sum. L goes from 0 to q minus 2 of e to the 2 pi I m over q minus 1 to the L power. What sum is this? It's a geometric series. And the nice thing is you evaluate it at 0, and then you subtract off its value at 1 more than this, which is q minus 1. So you'll get 1 minus 1 upstairs. So the sum is going to be 0. The only time it's not 0 is if m itself is 0. If m is 0, then every term is 1, and this is going to just become q minus 1. So this is equal to q minus 1 if m equals 0 and 0 otherwise. And this is by the geometric series. And so again, when m does not equal 0, you just evaluate it at first term minus 1 more than the last term divided by 1 minus the common ratio. As long as m is not 0, the common ratio is not 1, so the denominator is not 0. So I urge you just go through, do the calculation. What this does is this sum detects whether or not our number is 1. If our number is 1 mod q, we get q minus 1. If our number is not 1 mod q, we get 0. So this is a detection. Detects if g to the m is congruent to 1 mod q. And now you can begin to see how this might be useful for Dirichlet. We're going to use this to detect primes congruent to a mod q. And it turns out this Legendre symbol, this p on q, it turns out that's a very special quadratic character. It's a very special one of these characters. And in fact, it's the most difficult character to analyze. And it plays a crucial role in what's going on. I'm not going to go into all those details, but I just want to give you a rough sense of why we care about all the stuff in chapter 3. I think chapter 3 is well written, but if you're not a professional number theorist, you might wonder why we care so much about quadratic reciprocity. Why do we care so much about being able to do this? It turns out that there are really beautiful formulas involving primes congruent to a mod b that use these characters. And so what I want to do now is I want to look at, we'll have L, S, chi L, and this will be a sum, and goes from 1 to infinity, of chi L of n over n to the s. And it turns out this is the same as the product over primes of 1 minus chi L of p divided by p to the s inverse. Real part of s greater than 0. We can actually do a little bit real part of s greater than 1. I believe we can actually do a little bit better here because we have cancellation, but real part of greater than 1 is fine. Okay, so this is the thing we want to look at. What do you want to do now that you have this relation? What do you want to do? Take the log. So we have the log of L, S, chi L. It's going to be, I have a log of the sum. Screw the log of the sum. I don't want to do that. I'll take the log of the product. So I'll have a sum over primes. And I'm going to have a negative coming down from this. And I'll have the log of 1 minus chi L of p over p to the s. And I'll recall the log of 1 minus u is negative u plus u squared over 2 plus dot dot dot. So I'm going to Taylor expand the log. Because I really don't want to deal with the log of 1 minus a character. I want to get the characters. So this is going to be equal to negative and negative will reinforce. Wait a minute, actually, I think for the log of 1 minus, it's all minus signs. So I will get the sum over primes, chi L of p over p to the s plus something that I'll call good of s. And again, this is the 5-minute spiel. If you want the longer spiel, take the analytic number theory classes that will be offered next year. But the higher order terms, they don't really matter. You can show that they're good. All right, so this is the log of L, S, chi L. I want to study primes congruent to A mod Q. If I sum this over all characters, I'll get the primes congruent to 1 mod Q. I can attack primes congruent to 1 mod Q. But I don't want primes congruent to 1 mod Q. I want primes congruent to A mod Q. What could I multiply both sides by? I'm sorry?
By A.
Almost by A. A is just a number. It should somehow involve the character. So I'll multiply both sides by chi L of A inverse. Log LS chi L is equal to, and leave a little bit of space, the sum over P chi L, and because it's multiplicative, it'll be P A inverse over P to the S plus, I'll call it good tilde of S. And there should probably be like a little L subscript here, because it could be different for different L's. Now, what do you think I should do to both sides? We're one step away. So we want to somehow detect when P is congruent to A mod Q. Well, that's the same as P times A inverse is just 1 mod Q. What should I do to both sides? So what result do we have from before? So what do we have? What way do we have to detect? How were we able to detect the relation we wanted? What did we do?
The geometric series.
Yeah, so how did we get the geometric series? We summed over. What did we sum over?
0 to Q minus 2.
Yeah, what variable did we sum over?
Just L.
We summed over L. We summed over all the characters. So let's sum. L goes from 0 to Q minus 2. And I'll divide by Q minus 1, the number of characters. And so I'll put a 1 over Q minus 1. And I'll sum. L goes from 0 to Q minus 2. One of the biggest tools we have in number theory is switching the order of summation. You have to show it's justified, but what we want to do is we want to do the sum over L first. And if we do the sum over L first, we'll also have a sum over here. That still stays good. When we do this sum, it's going to be 1 if P is congruent to A mod Q and 0 otherwise. Because it's only 1 if P times A inverse is 1 mod Q. So if P times A inverse is 1 mod Q, P is A mod Q. So we get that the right-hand side is the sum over primes congruent to A mod Q of 1 over P to the S plus good, I'll do double tilde of S. And now notice this. If S is a positive real number, I'm summing the reciprocals of positive numbers. And I'm only summing over the primes congruent to A mod Q. If I can show the left-hand side is infinite, if infinite, what can we deduce? So if the left-hand side is infinite, what can we deduce? Then the right-hand side is infinite. Implies right-hand side is infinite, therefore infinitely many P congruent to A mod Q. And that's a rough sketch of Dirichlet. This is why we care about the homework problems I'm giving you. This is why we care about the structure of Z mod PZ star. This is why we care about these characters in quadratic reciprocity. Okay, so this is a good place to stop.